Are you plugged in?
Yep.
It's got the reverb on. Go ahead. Welcome back to episode 4 in Topics in ECE, where we're trying to understand a schematic diagram. So here's where we got to in part 1. We were looking at this schematic, which is a piece of a guitar amplifier. And the guitar amp has 2 input jacks, jack 1 and jack 2, plus several controls. And we've been applying circuit theory that we developed in episode 3, specifically voltage dividers, together with some circuit theory from part 1, linearity and Thevenin equivalent circuits, to figure out what's going on here at the input. And what we determined is how to analyze R1 and R2 in the connections here to understand what goes into the rest of the amplifier. If there are 2 input signals, as represented here with 2 different frequency sine waves, for example, then those 2 are summed together, but because of some voltage division, we found that they're also attenuated by about a half, so the resulting waveform coming out looks something like this. We also looked at an op-amp-based amplifier in the circuit and determined that it had a voltage gain of 6, and so this signal gets bigger. We, however, conveniently skipped over a few of the complexities, such as exactly how is C1 working here, and these 2 capacitors here were kind of ignored. And we also skipped D1 and D2 at the input. So today we're going to set that right. Here's what we're going to cover. As we'll see, those 2 diodes at the input perform what's called input overvoltage protection. The capacitor is an AC coupling capacitor, but only for certain frequencies. And we will figure out what frequencies it works for using what I call frequency-dependent voltage division. And we're going to do a little bit of math, but don't worry about that. We're not going to do a whole lot of math, but we do need to tie this back into circuit theory. And then the rest of these topics, as you'll see as we go along. So let's continue our journey in understanding circuits. We'll start here with the diodes and progress through this amplifier, talk about its frequency response, into this section, which in this guitar amp is a distortion generator, and concluding today with the tube amp. So in part 1, we discussed how to analyze what's in the gold circle here, figure out what it's doing, and importantly, replace it with a simplified circuit that makes subsequent analysis of circuitry easier. Specifically, we're replacing it with a Thevenin source model as shown in the circle on the right. And that Thevenin equivalent circuit is composed of a voltage source in series with a resistance. Now, the voltage source is shown as a sine wave, but in general it represents any waveform Vn of t, which in our case is composed of the time-varying input Vn1 of t. I'm specifically not including the t here. That's implied. These are time-varying waveforms. And Vn2 of t. And when we analyzed the circuit, we found out that the composite voltage, or the Thevenin voltage Vn, is the sum of the 2, but they were divided by 2 because of voltage division. We also showed how the source resistance can be found, and in this case it was 11 k ohms. So here is our circuit to be analyzed now. It's much easier to analyze than this whole thing. And I could leave both the original circuit and this circuit up here, but that defeats the purpose. Remember, our goal is to simplify things as we go. And the Thevenin source model does that for us. Now, some of you may know about diodes, and some may even recognize Zener diodes. If you don't, here's all you need to know. A diode is a symbol something like this. It's composed of semiconductor, specifically what's called p-type and n-type, blah, blah, blah. But all we need to know here is that it allows current to flow in one direction. You see this looks somewhat like an arrow, so it allows current to flow in this direction. It generally blocks current in the other direction, so this second one at the bottom here would block current from coming down. And so there would be no current flowing through this leg and whatever Vn is would go on to the rest of the circuitry. However, all diodes, when they're blocking stuff, have a limit as to how much voltage they can withstand. And if the voltage gets bigger than that, then current will start to flow. In fact, it will flow a lot. So what happens here is Vn, if it's a small enough sine wave, it will just go on through. But if it's large, as the voltage rises, you can see it on the right-hand side, it will eventually get to a level that's big enough to cause Zener 2 to conduct. And when it does, the voltage will stop rising. And that's because you'll get a voltage drop through RS here that prevents it from rising anymore. So the result is the output waveform is this, and it's a clipped version of the input waveform for sufficiently big input waveforms. Again, small ones, they go right through. So this thing, all it does is protect the rest of the circuitry downstream from this point from seeing too large a sine wave. It clips it. But ordinarily in this application, the voltages coming from the guitar pickup are maybe a volt maximum. And these may be 6-volt Zeners. I didn't look them up. But nothing's going to happen because the voltages at the input are too small. If someone does something silly like plug the output of a previous guitar amp, the speaker output, into the input jack here, it will not blow up this integrated circuit because this will protect things. Okay, so the next stage of the circuitry is here. And in part 1, we focused on what happens at what's called midband, basically audio frequencies that this guitar amp is designed to process. And we said, without proof, that C1 just passes the signal on. So it moves from the junction of R1, R2 on over to R3 and into the amplifier, IC1. Also, and this is important, we said that the impedance of C2 at those audio frequencies is so high that when it's in parallel with R3, the net result is basically just R3. C2 we could ignore. Similarly for C4 in parallel with R4. And for C3, this is a very large value. It's 2.2 microfarads, which at audio frequencies is large enough that this is just a connection to ground. We didn't prove that, but we're going to do that next. So analyzing this circuit at midband, we have an op-amp, signal going into the non-inverting input of the op-amp, the output of the op-amp with a resistor R4, and then a resistor R5 to ground. And we had analyzed that previously and figured out that it has a gain of 6. In part 1, we also briefly looked inside integrated circuit 1 here and saw how complicated it was. But using Thevenin's theorem, we figured out that we could replace all of this circuitry, including the detailed circuits inside, with this simplified model shown on the right. At midband, all of that complicated circuitry reduces to a resistor to ground at the input side of the amplifier, called Ri, which in our case was 270K, and output circuitry, which is composed simply of a Thevenin model, where the voltage is the gain times the input voltage. And it has an output resistance, which would be the Thevenin resistance. And that would allow us to figure out what would happen if we loaded it. In this case, the output resistance was 0. And so even though there's like 1.5K loading the circuit, we can ignore that. So we've simplified our life tremendously. So let's go back and talk about C1. Why is it there? And what happens if you're not at midband, whatever that is? We said it's audio frequencies. Let's find out. So here's a circuit that's going to allow us to figure out what's going on with that so-called coupling capacitor. To the left of it is the Thevenin equivalent of the input circuitry of the guitar amp. To the right of it is the input resistance of the amplifier. And this is all we have to analyze. And we're going to use voltage dividers to figure it out. Let's start with what I call full coupling. That's where the impedance, ZC means the impedance of the capacitor, that's where its impedance falls to 0. I haven't proven that, but you can get it from these formulas down here if you know a little complex math, blah, blah, blah. But for right now, just take it as a given that high frequencies go through capacitors. That's what everybody says. That means ZC is 0. So we just have the source voltage Vs driving into a voltage divider composed of Rs and Ri. And we know the voltage divider formula, and I've written it over here on the right. So at sufficiently high frequencies, Vn is not equal to Vs. There is some voltage division that takes place, and that's due to the resistors at the input circuitry of the guitar amp. But Ri is 270K and Rs is like 11K, and so basically there's very little voltage division. If you want to know the exact value, you can figure it out over here. But it's more than 90% of the source voltage gets into the input. And that's at high frequencies, where the impedance ZC goes towards 0. At the opposite extreme of frequency, which would be zero frequency, otherwise known as direct current, the symbol for a capacitor, of course, gives us a hint as to what's going on. These capacitors are normally composed of a couple of plates of metal that do not touch. And so DC, or direct current, cannot go through them, and so ZC, the impedance, is infinity. More precisely, it's minus J times infinity. And all that means is that the voltage and current are out of phase by 90 degrees. That's what the minus J does. But that doesn't matter because there isn't any current, so minus J infinity and infinity are the same. So over here on the right, I've written the expression for Vn in terms of Vs and the three impedances, Ri, Zc, and Rs, using a three-component voltage division, which is just Ri divided by the sum of these three, which we see in the denominator. But that denominator is basically infinity. So we have Ri over infinity, which is 0, which is a very complicated way of saying what we already knew, that the capacitor blocks DC, and if there's no current flowing here, there's no voltage drop across Ri, and the output voltage is 0. Okay, now let's talk about OK coupling. What does that mean? That's my term for there's enough coupling through the capacitor that this signal Vs basically makes it over to Vn. It might be attenuated a little bit, but for a guitar amp, nobody's going to even notice. If it's attenuated to about a half of its previous amplitude, it's barely audible difference in volume. And that's going to happen at some frequency between DC, or zero frequency, and some high frequency, but we want to know what the value of that frequency is. And we can get that by looking at XC, the reactance of the capacitance. So this is a formula many of you know. If you don't know, you can look it up on the internet. Just search for capacitor reactance. And whenever you see a new formula like this, if this one's new to you, plug in a few cases and understand what's going on. If we plug in 0 in the denominator for the frequency, then we have 1 over 0, and we get that the reactance is infinity. That's what we just talked about at DC. If we plug in a very, very high frequency, then the denominator gets very big, and the 1 over big thing gets small. So that's what we talked about at high frequency. But I'm going to assume we plug in a very special frequency called the corner frequency, which is the frequency f, where x sub c equals, in this case, Ri plus Rs. When we do that, here's how it plays out. The voltage division is now Ri over the sum Ri plus Z sub c, which I have written this way, plus R sub s. But when we're at the corner frequency, where the capacitor reactance equals Ri plus Rs, this term, in parentheses in the denominator, will be minus J times quantity Ri plus Rs. You can write that down on a piece of paper and do a little factoring. Just treat J as another number or variable, and we can move from this expression to the one below it. Now, if you're uncomfortable with all this J stuff because you really haven't messed with complex numbers, or you haven't realized that electrical engineers use J instead of I in complex number math, the net result is shown here. We end up with Vi equals Vs times the quantity Ri over Ri plus Rs times another term. Without that other term, it would just be what we would have for full coupling. So this last term multiplies what we would normally get with full coupling. What does it multiply it by? Well, if you crunch complex numbers, there are some things on the internet you can use to do that. And you plug in 1 over 1 minus j, or 1 over 1 minus I if they're doing it that way. Then this number is 0.7071 at an angle of 45 degrees in polar form. What does that mean? Well, it means that the VI value is 70.71% of what it would be for full coupling. And it's been shifted by 45 degrees in phase. So even though this capacitor is here, most of the signal, 71% of it, gets on into the next part of the circuitry. It's shifted by 45 degrees. If you're an audio person, you may know that human ear and brain aren't really sensitive to phases in general. And so that doesn't matter. We don't care about that. What we care about is that at the corner frequency, the amplitude of VI has fallen from what it could be with full coupling at much higher frequencies to 70% of that, 71% of that. And that's enough that you can hardly even detect any change in volume. So we get pretty good coupling, or okay coupling is what I'm calling it. So moving back up to the top level, why is C1 here? And what is that magic frequency, FC, where it gets coupled pretty good? Well, the answer to the first question is, we've already said, C1 blocks DC. So if you were to plug in something into the inputs over here that had a lot of DC on it, then it would not get into IC1. If it did, it could cause the output of IC1 to what's called saturate. This output could be very high or very low, close to the supply rails. More importantly, then any audio on it would not get on to the rest of the circuitry. So you're stripping the DC off is what this guy is doing. We know that at sufficiently high frequencies, however, the signal will go on through here. So this will pass high frequencies. So we call it a high pass function. And the corner frequency that we're searching for is given by this expression, which is basically the corner frequency is 1 divided by 2 pi RC, where in this case R is RS plus R3. So RS is the Thevenin source impedance over here on the left that we used to replace all of this. It's 11K, and R3 is here. And crunching the numbers with 11K and 270K, and then 0.047 microfarads, works out to 12 hertz. That's good, because that means any audio frequency that we can hear is going to get on through to this amplifier. Yay! Lastly, before we move on into the amplifier circuit itself, what is C2 doing? Well, recall that the reactance of a capacitor, which is the magnitude of the impedance, is 1 divided by 2 pi FC. So if you plug the numbers in and you use audio frequency for F here and 100 picofarads for C, you find out that this number is like a megaohm or more. And in parallel with 270K, the net result of those two things in parallel, something really big, several megohms maybe, in parallel with 270K is just about 270K. So it doesn't really do anything at audio frequencies. But at sufficiently high frequencies, the impedance of this capacitor is going to fall because F is going to rise. If it rises enough, say to 100 kilohertz or a megahertz or more, then the reactance XC here will be much less than 270K. So whenever two things are in parallel, the small value wins if they're widely different values. So if the impedance of C2 falls to, say, 10K at sufficiently high frequency, then this just looks like 10K. Meanwhile, the input, remember the Thevenin source is a 11K ohm source resistance, so now we get voltage division with it. So as the signal goes through R1 here, this capacitor, C2, will do what we sometimes call short the signal out. So it basically forms a voltage divider. But that only happens above 150 kilohertz. And the reason it's here is because the input signals that come from the guitar pickup can be exposed to what we call radio frequency interference. If there's a strong radio transmitter nearby, like a wireless mic or something, then it could inject enough signal in here to disturb the operation of this amplifier. So what we want to do is short out those signals, which maybe is 70 megahertz or gigahertz. We want to short those out so they don't get into IC1. And provided they're sufficiently higher than 150 kilohertz, we're fine. We have protected the amplifier, the rest of the downstream circuits, from both DC and very high frequencies, radio frequencies. Audio frequencies will just go right on through here and get amplified. So let's look at that next. So the next stage is built around IC1, and as we've said before, it forms an amplifier with a gain of about 6. At least at midband, or in our case, audio frequencies. It also provides one other very important function which is not explicitly shown on this diagram. In addition to gain, it also provides what we call impedance buffering. Remember, the output impedance of this circuit, when we model it using Thevenin's theorem, is approximately 0. And that's important because it means that no matter what we connect this signal at the output here to, within reason, it won't form any significant voltage division. So whatever we found for the gain from the inputs up to this point is not going to be affected by what we connect here. So this 4.7K, this 1.5K, this 0.1 microfarads, we can ignore all of that when we're analyzing what goes on here. Now, with the tools and concepts we've just developed, we can look at the reactance XC of these capacitors, C4 and C3, and understand what's going on with them. At audio, C4 is essentially not there, and C3 just connects the bottom of R5 to ground. But what happens at other frequencies? Well, we can use what we've just learned to figure that out, and I've summarized it at the bottom here. Somewhere around 20 kilohertz, C4's impedance reduces to the point where it's lowering the net combination of R4 and C4, and that reduces the gain. So the gain reduces above about 20 kilohertz. C3, which normally connects R5 to ground, increases in value at a sufficiently low frequency below 50 hertz. Why are they there? Well, that's a good question. I'd be willing to bet that if you just took C4 out, and if you just connected the bottom of R5 to ground, this circuitry would still work fine. So their function is subtle, I think. Of course, you could argue that there's no reason to have anything above 20 kilohertz because we can't hear above that frequency, and no reason to go below 50 hertz because, well, the speaker in the cabinet maybe doesn't go below that anyway. So maybe they're just put there for good measure. One other reason for C3 is that this op-amp, as we'll see in maybe another episode in the future, has a little bit of bias current coming out here which goes through R3 and creates a DC offset. And if we amplify that, it could, well, it's not going to saturate the amp because when I calculated it for the device being used, it's only about 1 volt maximum here. And downstream circuits have AC coupling capacitors to DC block. And so I don't really know why C3 is here. Moving on down the signal processing chain, the next thing that comes up is what's in the red box. And using the analysis techniques we've just talked about, we can figure out what's going on here. I'm not going to go through this in detail. You can feel free to freeze the slide here and read through this if you like. But in a nutshell, think of the output of the op-amp as a voltage source coming in here at test point 1. Then, at low frequencies, we can ignore C5, and we have a voltage division of 1.5K over 1.5K plus 4.7K, assuming downstream loading can be ignored, which it can because it's about a megohm if you examine those circuits. But at higher audio frequencies, C5 is in parallel with R6 and couples the signal directly through, so we don't get that voltage division. The response then overall is a bass cut. Bass frequencies are reduced as they go through here or to put it another way, treble frequencies are increased relative to the bass. And given the values computed, I estimate it's about 12 dB. Not a biggie, but it would change the sound of the amplifier a little bit. So we've made it all the way through to this point. In fact, we've made it all the way through to at least this point, because what's this? It's an AC coupling capacitor, and that's a 1 megohm resistor for bias currents in IC 1B. So we know what this is. We've covered all of these things. So we're halfway through our journey. We've parsed half of this schematic into the functions. What's going on as the signals pass through. The pieces left are what's in red here, and the yellow and the blue. And those are what I'm labeling gain and distortion generators. Gain because this is another amplifier. In fact, this is where most of the amplification begins in this product. Up to the input of the red circuitry here, the net gain is about 1. We have a half here if both inputs are used or if this lower input is used. And then we have a gain of 6, but then a gain of 0.25 for our bass cut treble boost. Trebles get a little bit more. And then it goes on into this next circuitry. And obviously there's a lot here, but hopefully we can leverage some of what we've talked about so far. In addition to that, I'm going to be a little bit briefer in these sections. First, a quick overview. Remember, signals coming in here at the upper left. There is a potentiometer here. And if we turn that potentiometer all the way up, meaning fully clockwise on the front panel of the amplifier, then this tap point is at the bottom. And the circuitry over on the left here is an analog switch. We'll cover that briefly in a minute, but just imagine that this point right here is now an AC ground at this node at the bottom. That means that R13 is connected to ground. So the signal comes in on the non-inverting input. The op-amp has a feedback resistor R14 and then a resistor to AC ground R13. And using what we've learned in previous episode, 1 plus R14 over R13 works out to a gain of 150 at midband, which is plenty to take an audio signal of about 0.1 or 1 volt here and make it big enough to actually saturate the output of this amplifier. So in general, we won't run it fully clockwise. We'll dial the gain back with this potentiometer. But if you're a guitarist, you know that you may not dial that gain all the way back. Sometimes we want a rather harsh sound, a gritty sound, or whatever your favorite adjective is there. So we might run this gain pretty high to make sure this thing does saturate and clip. And that's what these diodes are for as well. And under that situation, we will get what's called odd harmonic distortion. We can actually turn that distortion off with a control on the front panel that will affect what this transistor here is doing, whether or not it's AC grounding this point. This is playing the role of what's called an analog switch, and if we turn off that analog switch, then this is no longer AC grounded, and this reduces to a gain of about 1. At which point, the main gain is supplied by these vacuum tubes. And why are they there? Well, everybody loves vacuum tubes, for one thing, if you're in audio. And why is the reason for that? Well, they produce a different kind of distortion, usually termed in the literature even harmonic distortion. And we'll take a look at that. But before we do, I would highly encourage you, if you're interested in this, to look at this video. You can go to this link, or you can just search YouTube for tube, solid state, or software, amp blind test challenge by Daryl Braun. And he does some really fun and interesting demonstrations of the different types of distortion, from solid state amps to tube amps and something called software processing, sometimes called digital signal processing. So I would very much encourage you to go to this and listen to these tests that he does. He says, can you hear the difference between a tube amp, solid state amp, and amp modeling software? Take the challenge and find out. Our role in this video, of course, is to figure out how we actually do this electronically. How do we make the different sounds? How does a tube amp work? How do these switches work? So that's what we're going to cover in the remainder of this video. But that's a lot. So we're only going to scratch the surface in the next few minutes that remain. We'll talk about these junction FETs, JFETs. And we'll talk about the tube amplifier and issue the obligatory warning. There are very high voltages here, so don't mess with this unless you know what you're doing. But we can at least safely discuss how it works electronically. And then there are more circuits to come. So we're not going to cover the ones shown here today. We'll briefly look at these in the next few minutes, but there's no way that we can cover all of this. Some of you may recognize some of the circuitry here in a power supply, for example, but some of you may not. So, how could you learn more? Well, there are many different ways to learn. From this video and the other videos in this particular series, as well as thousands of other videos on YouTube, the associated website for this channel, and many other websites, and of course books. In the university where I taught an Intro to Electrical Engineering course as well as more advanced electronics courses, these are a couple of the books that we used. And I particularly love this one. If you have at least some background in electrical engineering, and I suspect you do if you've gotten this far in this video, this is a great book. It's illustrated very well and covers a wealth of topics, even more than the one that we used in the electronics course at the university. So let's overview some of what you may find in those sources of knowledge. Here's our tube amp. But there's also this solid-state switch. This particular one is a junction field effect transistor, JFET. It's actually a P-channel device. Even though the schematic showed it as an N-channel, I fixed it here with the arrow going out based on the part number they gave. The purpose of this guy is either to ground this node right here or not. So either connect this to ground or disconnect the circuit right here. And that's done based on a DC voltage placed at this terminal here, A, based on some front panel controls. The device used in this particular amplifier, this is a J176 part. So you can type into Google or whatever your search engine is, a J176 data sheet. And you might get something like this over here on the right. Except that this is the J112, and that's what they're using on the left in this particular application. So this is an N channel, this J176 is a P channel. All that means in this application is it changes the polarity of control voltage that you apply here to get this thing to turn on or off. At university, you'll spend an entire semester examining solid-state devices like diodes, bipolar junction transistors, JFETs, MOSFETs, blah, blah, blah. But you can go to the Wikipedia page and they have a decent walkthrough of what this particular device is doing. It has a source at the bottom, a drain at the top, and a control gate. If you don't apply any voltage to the gate, then there is what's called a channel here where electrons can flow through. Or what are called holes instead of electrons if it's so-called p-type. We don't care about that right now. Just think of this as a conducting channel. If you apply a voltage here of the right polarity, then this yellow region will extend all the way to the right and shut off that channel. The yellow is what's called a depletion layer, and it's an insulation. So it would shut off the channel, and you'd have an open circuit, and this node on the left here would not be connected to ground anymore. When it's on, how much is it on? Well, that's what you need the data sheet for. And I looked it up. It says static drain source on resistance, 30 or 50 ohms. That's for the J112, which is used over here, the N-channel version. And that means that this point is not completely AC grounded. It's got 30 or 50 ohms from this point to ground, but compared to the 100K ohm, it's essentially tied to ground. That's what matters in the design. Now, let's assume that this JFET analog switch shown in this diagram is on, which means that this point here is connected to ground. Then we have an AC coupling cap and a volume control. You can ignore 114. I'm not sure what R114 is doing. I think it's just changing what's called the taper of this potentiometer. But it still works as you'd expect. When you're fully clockwise, then this wiper is connected to the top here, and the signal goes in unattenuated. But if your volume control is turned counterclockwise, then it's down here. You get a lot of voltage division, and it cuts the signal level. Anyway, the amplification begins over here with an AC coupling cap, C11, this R16 resistor, and R17. There's no voltage division here to speak of because you got 1 meg and 47K. So signal pretty much goes into what's called the grid of this tube. Then there is amplification from the grid to what's called the plate, pin 6 up here. And in this particular design, it's about a gain of 60. But there's an explicit voltage divider over here, which cuts that back by 1/3. So we got a gain of about 20 from pin 7 to pin 2 of this dual triode vacuum tube. And then on this side, we have a gain of about 60. How do I know that? Well, you can look up much of that from the data sheet. So the net gain from the input of this vacuum tube amplifier composed of 2 tubes is about 1200, about 20 times 60. And that is enough to make this thing go into significant distortion, to clip the signal at the bottom and top, and also to have a cool vacuum tube in the amplifier. On this slide, I've tried to provide a hint of how that even order harmonic distortion can happen. If you look carefully at what's called the plate current waveform here, and the overall plate voltage, this is the output voltage waveform, you'll see that they're not perfect sine waves. At the output, the bottom half cycle of the sine wave is a little bit more spiky than the top half. And if we were to crank the gain up a little bit more, this would flatten out before this probably reached the bottom down here. Eventually it would flatten out as well. And you get different sounding distortion. And I would encourage you to listen to these tests and see for yourself what those sound like. So that's it for part 2 of episode 4. We've made our way all the way through this portion of the schematic for the guitar amplifier. More importantly, we've covered many topics that are important in understanding just about any analog circuit. We've leveraged voltage dividers that we saw in episode 3, introduced linearity in Thevenin equivalent circuits, looked at how voltage amplifiers can be modeled and simplified, and learned how to parse schematics into block diagrams. Along the way, we met some common analog subcircuits, not everyone by any means, but many of the common analog subcircuits, including RC circuits, coupling capacitors, tone control circuits, and so forth, and JFET switches and tube amps. But electronics is a gigantic field with literally over 100 years of background, and it takes time to learn everything. In fact, nobody learns everything, but that's good. That means we can always continue learning. And here are some different ways to learn again. In the future, we may produce some more videos in this series. In particular, look at different operational amplifier circuits, but there are many of those out there already, so you could go to other videos on YouTube, or maybe this book, which has really good information in it. And no, I don't know the author or have anything to do with this book. I just found it to be a really good book when I was teaching these courses, so I recommended it to students, both in the intro course and the Electronics 2 course that I taught. I did not do circuit theory. Other possible future videos is to look at operational amplifiers and detailed design. We have to know things like the gain bandwidth product, how high a frequency can these things process, the bias current that we briefly touched on today. There's limitations on the output voltage swing, how high, how low can it swing, usually limited by power supply rails, but also by the internal op-amp design. And how much current and ultimately how much power can these things put out. In the guitar amp that we looked at, the circuits that we discussed today precede this last part of the circuit before the speaker, which is a power amplifier. So you can get up to, I think, 70 watts or something for this particular one. This is actually an operational amplifier. but it's done with discrete parts. So we might cover something like that, but that's pretty involved. We will probably cover power supplies in the future. And perhaps some big circuit walkthroughs, looking at the circuitry like what we've covered today for different kinds of circuits, and talking about what each part does and why it's there. So until then, thank you for watching this video, and I hope it's been useful to you. Bye. All right, so this is the Pile Pro 60 watt amp, which is claimed to have some buzz in it. So we're going to plug the cable in first to the unit and see how much it buzzes. All right, so, oh yeah, definitely buzz. Well, so what are you doing? Okay, all right. So with it disconnected, it's certainly buzzing some. But let's go ahead and plug it in and see if it buzzes when we get plugged into the guitar. I'll turn the volume down, maybe. Are you plugged in?
Yep.
Actually, I didn't turn the volume down, and I think the buzzing's gone.
Yeah. It's got to be pretty
It's got the reverb on. Go ahead. Okay, that's pretty loud.